Okay, so let's start. So the quiz will be on Sunday. Today's lecture is not included, so it's going to be everything until today's lecture. Okay. So, okay, so take a seat. Take a seat. So today I'm gonna first of all I'm gonna talk about transmission environment. After I finish teaching this part, you should learn why when you send, if you have a cable like this one, if you send the signal in a certain way, the signal you are going to receive here will be somehow different from this signal. Same thing here. If I send this signal analog or digital, so after I finish teaching this section or this part, you should understand why when I transmit a signal analog or digital, the signal I'm going to receive here is not going to be exactly, take a seat, it's not going to be exactly same signal, but there'll be some distortion in this signal. And this is something normal, okay? So that's what I'm going to explain in this part. So actually, that's what we call transmission impairment. The reason for this impairment, I'm going to talk about three reasons. The first reason is attenuation. The second one is distortion. The third one is noise. So because of these three reasons, as I said, when you transmit a signal here, what you are going to receive here at the other side of the cable or of the medium is going to be distorted signal. It's not going to be exactly same signal, okay? The first thing I'm going to talk about attenuation. So attenuation means if you have a cable this way, as you see here, if you have a cable, this is 0.1 and 0.2. If this is the original signal, I'm gonna here in this point, I'm gonna receive a signal. It's the same shape, so there is no distortion. It's the same shape. However, the signal is attenuated. It lost some energy. This is because this is something normal. When this signal is propagated from here to here, this signal is facing resistance. Okay, so in order to move from here to here, and because of facing resistance, the signal is going to lose some energy in the form of heat. That's why some cables, you can find some cable have some kind of warm, they are warm or heat. So they are going to lose. So this is something normal. Okay, we cannot do anything about it. Okay, so what you should understand, for a signal to propagate from a certain one point to another point on the cable, so actually this signal is going to be attenuated. Attenuated means it's going to look no distortion. So it's the shape of the signal is the same, but it's a signal lost some energy. Okay, in the resistance of the medium. Okay, in the form of heat, and that's something normal. Okay, so what can we do about this? What can we do is I can put here amplifier. So this amplifier is going to amplify the signal again. The signal is going to gain energy again. That is why in case of bus topology, in bus topology, we have here, this is one way to make a lane. So one way to make a lane is you have a bus this way, or a cable or bus, you can connect several computers together this way. Okay, so in this case, they are gonna tell you this cable, there is a limit on the length of this cable. There is a limit. Okay, why there is a limit? Because of the attenuation. So if you send the signal here, we have to make sure the last one here can understand, or the signal is not very attenuated. Otherwise, if the signal is very attenuated, so you're not going to be able to use this signal. You understand what I'm saying? So that's why always, as I told you, there is a limit on how big is this cable. And in case, so this is in case if you need a bigger cable, if you need a bigger cable, you have to put here what I explained in chapter 1, repeater. So repeater is kind of amplifier. So this repeater is gonna do the amplification. So that the signal it has to go has to transfer. Is gonna go through this second cable here. You understand what I'm saying? Any question? Okay. So now, in order to measure this attenuation, we can measure it in two different ways. One way, as a ratio. I can say, if you have a cable this way, this is power 1 and power 2. When I say the signal lost 50% of its energy, 50%, that means B2 equal half of P1, right? The energy at P2, half of the energy of P1. That means it lost 50%. Is that okay? So I can, in order to measure this attenuation or amplification. So in case of amplification, if you have amplifier here, so I can say B3 divided by B2 equal 10. So what it means? It means I amplify the signal 10 times. So this ratio, if this ratio is less than 1, if B2 divided by B1 is half, this means attenuation. But if the ratio is greater than 1, it means amplification. Is that okay? So what I want to say, in order to measure this attenuation or amplification, we can use the ratio. I can say 3 times, 4 times, 10 times, or I'm going to use decibel. And I'm going to explain to you what is decibel. Also, I'm going to explain to you why sometimes or most of the time we like to use decibels than using a ratio. Okay, so let's see what is the idea here. The idea is this is the ratio B2 divided by B1. I told you I'm gonna convert 1 to what we call a decibel. This way. How can you do that? It's gonna be 10 log 10 of the ratio. You got what I'm saying? And then again, this is another way to express the attenuation or amplification. Another way. Okay. And I'm going to tell you what is the advantage of this one over using just a ratio. I'm going to tell you, okay? But anyway, let's see this example. In this very simple example, I'm telling you a signal travels through a transmission medium, and its power is reduced by half. So it lost half of its power. That means B2 is equal half of B1. B1 is the power at the beginning. B2 is the power at the end. So B2 is actually half of B1, okay? So P2 is half of P1, okay? So here, I want to express this one in decibel. So all what I did, as you see here, just a very simple substitution in this equation is going to be 10 log 10. This one half, P2 is half of P1, so it's going to be half. So the result here is going to be negative 3 decibel, okay? So before I take your question, so if I say the signal lost half of its energy, it's exactly the same thing. If I say the signal lost 3 or the signal suffered from -3, it's exactly the same thing, but just two different ways to express the same thing. You got what I'm saying? So if I say the signal lost 50% of its energy, or again, I can say the attenuation is negative 3 dB, and I'm going to tell you why this will sometimes, or most of the time, it's more interesting than ratio. You have a question? Okay, great. Okay. So again, as I told you, this ratio, if this ratio is greater than 1, that means this is amplification. If it is less than 1, this is attenuation. Okay. On the decibel level, at our side, for the decibel, if the decibel is negative, that means this is attenuation. If it is positive, that means it is amplification. Okay. Why? Because you know, in log, in case of log, okay, if this one is less than 1, so it's actually the log of any ratio less than 1, so it should be negative. Look, if anything greater than 1 is actually positive. Is that okay? Any questions? Great. So now let's see another example here. Here, I'm telling you a signal travels through an amplifier and its power is increased 10 times. 10 times. Okay, that means B2, and here I have amplifier, I have here B1. Okay, that means B2 equal 10 B1. we increased the energy. So I want to express it here in case of decibel. Just I'm gonna plug in the equation here, very simple in the formula, very simple. So here is gonna be 10 log 10 log 10 of 10. You know, in logarithmic, you know, if you have log A of A is equal to 1. And this is exactly the case now. So log 10 of 10 is 1. So now the result is 10 decibel. Is that okay? So when I tell you the signal is the power at B2, this is the most important thing you should understand. Two things I can express them in two different ways. So here I have B1, I have B2. When I say the power at B2 is actually 10 times the power at B1, it's exactly the same thing when I tell you from B1 to B2. So we actually we gained positive 10 GP. You understand what I'm saying? So positive 10 to B means it's 10 times. Is that okay? Any questions? Just two different ways to express the same thing, but I'm going to tell you why decibel is more interesting in this case actually. Okay. So actually decibel is interesting because if you see something like that, here we have a transmission medium and we have 0.1, 0.2. So from 0.1 to 0.2, there was negative 3 decibel. Is that okay? I told you negative means we lost attenuation. And then from 0.2 to 0.3, because we have amplifier here, it should be positive 70. Just from here to, and then from here to here, we actually left 3 GP. Okay. So now, if I give you this part, I give you this part, I give you this part. Then I'm gonna ask you to get end to end from here to here. Okay. The good thing about decibel is just a simple addition. You can add them together. That's why we like decibel. You got what I'm saying? So if you have this one, you have this one, you have this one. If I want to get it from here to here, from 1 to 4, you just add this one, from this one, from this one. That's it. Also the same thing. If I wanna get it from here to here, just it's gonna be -3 plus 4 plus 7. Sorry. 7, just add this one to this one. That's it. So it's going to be much easier than the ratio if you do it in decibel. Okay. So why we just add? Okay, I'm going to tell you why. Look here, what I'm going to show it mathematically, the idea behind it mathematically. For example, if you here you have B1, and then you have B2, for example, and you have B3 and you have B4. Is that okay? So if I want to get B1 to B4, okay, so it has to be 10 log 10 B1 divided by B4. Is that okay? It's the same thing when I say 10 log 10 of B1 divided by B2 times B2 divided by B3 times B3 divided by 3 by B4. Is that okay? For sure, because this one can go, this one can go, this one, and so on. Is that okay? And then, you know, in case of log, if you have log A times B this way, it's going to be the same as, can anyone tell me? Yes, log A plus log B. That's true. So yeah, if they are multiplied here, it's going to be added here. That's okay. Okay, so, and that's exactly what I'm going to do right now. So I'm going to say it is actually 10. It's going to be 10 multiplied by log 10 of B1 divided by B2 plus log 10 B2 divided by B3 plus log 10 B3 divided by B4. Is that okay? And then you can distribute this one. So this is decibel plus decibel plus decibel. Okay, guys. So again, what I'm doing here, number one, I told you, if you have a situation like this one, I know what happened between these 2 points. I know what happened between these 2 points. I know what happened between these 2 points. So if I tell you, if I ask you what happened from here to here, all what I said, you can just add the decibel together. Okay. So from here to here, as you see, the signal lost because it's negative, attenuated, amplified, attenuated. But from here to here, because this one is actually positive, is actually amplified by 1 dB. Okay, and then I told you why. Why, if you want to get it from here to here, you just simply add this decibel together, because we use the log. When you add log, it's going to be converted to multiplication. That's exactly what I explained here. So I just want to tell you it's exactly the same thing. Okay. Any questions? You just, yeah. So here I want to get from B4 to, I'm sorry, this one should be 4. I'm sorry, this one should be 4 and this one should be 1. Usually the last one before this one. So this one should be 4 and this one should be 1. Okay. Usually the last one divided by the first one, not the opposite. Okay. So if I do this way, I can get the ratio from here and then here and here. And then I can, this one can be 1 decibel, this one another decibel, another decibel. Okay. Anyway, any questions? Okay. Let's see another example. So here what I explained, how can we use the decibel to get the ratio, or to see what how much attenuation, how much amplification happen to the signal. Okay. Now I want to tell you something different here. Sometimes if you have a signal and this signal has watt in watt. Okay. Sometimes I want to convert this signal from watt to this. What I'm saying? It's exactly the same thing. I want to represent. I want to express the signal. Instead of what I want to make this. Okay. So the way we can do it, as you see here, it's going to be, if you have a signal and this, it's not a ratio. Now I'm not talking about a ratio. Okay. It's just one signal. Okay. If you have a signal and this signal is BM and this one is in milliwatt, I want to express the same signal in decibel. Okay. So I'm going to do this way. So this one in milliwatt. This one is the same signal, the same energy, but in decibel. Okay. So for example, I give you here example. Here I'm telling you I have the power of a signal. The power of the signal if is negative 30 decibel. Okay. So I want you to convert this signal from decibel to milliwatt. Okay. So very simple. Just the formula. This is the formula here, as you see here. So 10 log 10 BM in milliwatt should equal negative, or sorry, this one is in watt. Okay. So after you get it in watt, you can convert it to milliwatt. So you'll see right now. So the signal in watt is actually negative 30. Is that okay? So how can you calculate this one? For sure, you can divide by 10. So it's going to be log 10 BM equal negative 3. Okay. You can divide both sides by 10. Okay. And then for this one, you can use a calculator to get PM, or you can use the properties of logarithm. Okay. In log, if you have log, can anybody tell me log A of B equals C? Okay. So there is a relation between A and B and C. Can anyone remember this relation? B equal A to the power of C. Okay, this is logarithm. So here in log, if you have log A for B equal to C, so that means B, this one here, is equal A to the power of C. In order to calculate this one, I can just use this. I can use this one without the need for a calculator. So here I can say BM equal 10 to the power of minus 3 watt. Any questions? I think this one is in milliwatt. I'm sorry. So he told us in the very beginning we measure it in milliwatt. So he told us this number. When I got this number, I got it in milliwatt. So I'm sorry, this one should be milliwatt because this is what is given in the question. Okay. Any questions? So what I want to see here, if the energy of the signal, I can say the energy is 10 to the power of minus 3 milliwatt, or I say the energy is actually negative 30 in this. Just two different ways to express the same thing. Any questions? Okay. Then, yeah, sure. Sorry, is that always what? No, it depends on. But usually, because we talk about signals are very weak. So usually, number one, no, it can be in watt, or it can be in microwatt, whatever. It can be anything. But practically speaking, in communication, most of the time we are talking about very weak signals. So it's reasonable to, most of the time we are going to talk about milliwatt, microwatt, what I'm saying. But this formula is valid for anything. But what I'm saying, he's telling me when I measure this signal in milliwatt, that's what I got. You get what I'm saying? So this one was in milliwatts. That's why this one, when it's calculated for milliwatt, okay? So there is another thing here related to this part. Usually, so first of all, we agree on something now. We agree if you have a signal, this is a cable. So if you have a signal here, somehow this signal here, the signal will be weaker, right? And then the more distance we have is going to be more weaker. Does that make sense? So the longer is the distance, it's going to be weaker. You know what I'm saying? That's why distance is an important factor here. Distance is an important factor. That is why usually if you have a cable, I'm going to give you something like that. Okay, so I'm going to say in this cable is actually negative 0.3 decibel per kilometer. What it means? It means every 1 kilometer, the signal is going to lose negative 0.3 on the cable. Yeah, okay. So distance is an important factor here. So if this is a cable from here to any beginning, okay. So after 1K, so it's gonna be lose negative 0.3. Okay. So distance is important here. Okay? So let's see this question. So in this question, I'm telling you, I have a cable, and this cable is actually decibel per kilometer, and is actually this is in this cable we are going to lose negative 0.3 decibel every kilometer. Okay, and then I'm going to tell you here I have a cable. This cable is actually 5 kilometers. So the whole cable is 5 kilometers. And then I'm telling you at the beginning P1, and here is P2. At B1 it was 2 milliwatt at B1. Can you get the power? Can you calculate the power here? Okay, number one, I need to know how much I lost from here to here. I need to know how much power I lost from here to here. How can you know it? From this one. Because every 1 kilometer, I'm gonna lose 0.3. So in 5 kilometers, how much you are gonna lose in 5 kilometers? So what you are gonna lose here is gonna be minus 0.3 times 5, which is equal negative 1.5 decibel. So from here to here, you are gonna lose negative 1.5. Is that okay? And then you can just plug in the formula we had before. So I can say negative 1.5 equal 10 log B2 divided by B1. So now I know how much power you lost. I know P1. Now you can get P2 easily. Okay. Any questions? You understand what I said? Nothing is new. I told you the attenuation is a function. It can be function in the distance. Okay? Which makes sense because the longer the distance, the more the attenuation is. Okay. So let's remove this one. Yeah. So that's exactly what I did here. So number one, I have to calculate this one. How much power I lost from in the 5 kilometer from B1 to B2, which is this one. This number one. Number two, I already B1 is given to me. Now I can get B2. So here I can calculate B2 this way. Any questions? Okay. Regarding your question, so now is that in watt, in milliwatt, in microwatt, or in watt, or milliwatt, on watt? Okay. Look here. This is a ratio. So because B1 divided by B2 divided by B1, B1 is given to me in milliwatt. Okay. So for sure this one also has to be in milliwatt. So what I'm gonna get is gonna be in milliwatt. If I give you this one in watt, so this one also is going to be in watt. Okay, what I'm going to calculate is going to be in watt. If I give you B1 in microwatt, because it's a ratio, what I'm saying. So if I give you B1 in microwatt, what I'm going to get here is going to be in microwatt. What I'm saying? Because he already gave me this one in what? In milliwatt. So what I'm gonna get is also in milliwatt. Any questions? Okay. So the second thing I'm gonna talk about. So let me go back. I told you here in this part I'm gonna explain if you have a medium this way transmit a signal, the signal here is gonna be different. The first thing here I talked about attenuation. So attenuation again is not gonna change the shape of the signal, how the signal looks like, but it's gonna be reduced. Okay. Now I'm gonna talk about two other things. I'm gonna talk about noise. I'm gonna talk about distortion. You should both of them, all of these are gonna make the signal look different when it goes to the other side. Okay, but in different ways. This is because of the different reasons. Here the reason is actually resistance from the cable. Okay, so it's gonna lose energy. I'm gonna tell you what happens here and what happens here. Okay, so let's move to the next one, distortion. Okay, as I told you before, if you have a signal like this one, a composite signal, this signal actually is just a summation, of simple sine waves, as you see here. That's what I told you before. This has been proved already. This is a fact. Okay, so I can see this signal as a summation of these signals. Okay, that's what I told you before. Okay, so that means if I want to transmit this signal here, in order to get the exactly same signal on the other side, number one, all this component have to come to transfer to the other side. This number one. Number two, all these components should have the same, no change in the frequency, no change in the amplitude, no change in the phase. Okay, under these conditions, I can get here exactly the same signal. You understand what I'm saying? You remember when I told you before, it's if I want to transmit a square wave like this one, this is difficult. This is challenging. This is because this one has infinite frequencies. Infinite until a frequency is infinity, and there is no medium. That can pass infinite frequencies. You got what I'm saying? That is why I told you before, I'm gonna lose some component of these frequencies. I'm gonna lose some of them, and any component you are gonna use is gonna have impact on this signal. This is a bad thing. But what is the good thing? The good thing is some component have a very little impact. That's why if you look at the time domain, the frequency domain, if you look at the frequency domain, you see the first frequencies have big impact. But if you go as we go here, you find these ones have very little impact. So that means I may not need this component. Yes, there will be some distortion in the signal, but it's not severe. It's not severe distortion. It's still okay. Little bit impact because these frequencies have their amplitude is very little. Okay, if you have 1,000 plus half or plus 0.01, so still I can say it is 1,000. Makes sense? Because this one has a very little impact. Anyway, so let's return to our point here. The problem here, what we call distortion, the problem here is that because this component have different frequencies, okay, and every frequency is something normal. If you have a cable, so the speed, the propagation speed of these frequencies of this signal are going to be different because they have different frequencies. Again, these signals have different frequencies, and because they have different frequencies, they are going to have different speed. When you propagate them in the cable, when you put them in the cable, some of them are going to be faster than the other because they have different frequencies. Is that okay? Because of that, because they have different speed, some of them are going to arrive late. That is okay. So what is the impact of that? The impact of that, you can see it in the phase. So if you look here, this one, phase is zero. So this one is okay. But this one, the phase is zero. But if you look here, the phase is not zero because it's delayed. So this one came late. Okay, delayed. Okay. Same thing here, because this one, the phase is zero, but this one has a different phase because it is delayed. Okay, because of that, so now distortion already happened. Why? Because if you add this signal together, I'm not gonna get this one. I will get something different. because already the phase became different. That's why the signal here received is going to be distorted somehow. So again, the second type of the problem we have here for we call it transmission impairment. The second reason is distortion. The reason of this distortion is that the different frequencies are going to have different speed when they propagate. And this will make a distortion in the signal. Why? Because the component here are not going to be exactly similar to this component. You can see they are going to have different phases. So anything you change here is going to be reflected in the signal. Anything you change. So once you change the phase, the signal here is the signal here will be somehow distorted. Any questions? So this is the second reason. The last reason, we call it noise. So what is noise? I'm going to tell you simply what is noise. Again, you can see here different reasons. Here because of the resistance. Here because of different frequencies. They are going to make the phase of the signal. I'm going to change the component of the signal. This one is something else. What is this one? I'm going to tell you. So if you have a cable, and then I'm going to put a signal, something like that, this cable is going to pick up, okay, another signal, we call it noise. So now this cable is not going to have only it's not going to have only my signal, but it's going to have another signal coming from somewhere. I'm going to give you details. Just give me 1 second. I'm going to give you details. But what I'm saying, so here, I just want to show you the difference between the three. So here, this is my signal. There is another signal coming from somewhere. So what I'm going to get is the summation of these two signals. So it's going to be, for example, it's going to be something like that. Because I'm going to add them together. So what do you mean by the signal is going to come from somewhere? I'm going to tell you what I mean. The very, very forward or very easy case to explain it. As you know, if you have a wire and this wire has current, okay, electrical current, okay. So this one is going to create electromagnetic wave around it, okay. And if there is another wire, okay, so actually this wire is going to act like a transmitting antenna. This one, the second one is going to be like receiving antenna. So the second one here, by induction, so a signal will be generated here. This signal is going to be added to the signal you are transmitting on this line, okay? And this is actually the idea we use it for transformers, okay? Induction. This is something normal. So this is where. So again, in case of noise, all what I said in case of noise, you have your signal. There is a signal that's going to come from somewhere. They are going to be added together. Somewhere here is like, as I told you, it's going to be, for example, if there are electromagnetic waves around us. So for example, that's what I'm explaining here. This is your transmitted signal, but because there's already another signal coming from somewhere, I'm going to add them, I'm going to add them together, and that's what I'm going to do. Is for sure it's going to be different, somehow distorted, okay? Again, you should understand in communication, it's impossible to avoid noise. It's impossible to avoid distortion. Always this happens. But I'm not worried about that. I'm worried about if there are too much distortion. But acceptable distortion or distortion in a certain range, it would be okay. But too much distortion is bad. You know what I'm saying? So, you know, so the reason of this distortion, I already explained one reason, the induction noise. So the, induced noise. Induced noise here coming from devices such, motor appliances. So in our home, if you run a motor, all the appliances, even the projector, all appliances around us is gonna be like transmitting antennas. They transmit electromagnetic field around us. Okay, so because of these appliances around us that act as a sending antenna, so this actually is gonna generate noise here on the cable. There is another thing here, we call it crosstalk. In crosstalk, so usually, and you take a seat quickly. Usually, if you have a cable, you have wires here, So it's exactly the same idea. One wire can have impact on the other wires. So one wire is going to make transmit electromagnetic field. The other one, so one wire is going to act as transmitting and sending antenna. The other one is receiving it. So that's why in network one, you were told sometimes if we twist the cable, we can reduce the impact of crosstalk. The other thing, we call it thermal noise. This thermal noise, it's something related to the nature of the material, it's actually due to the random motion of electronics in the wire. For some reason, the electronics have some random motion, okay? And this can create also an extra signal, okay? So this is different from what we have here. Okay? There is nothing here. Also, one of the reasons here is what we call impulse noise. So let's see what impulse. Impulse noise means a spike of a signal with very high energy. Okay, in English, when I say spike, so something happening quickly. So this is spike. Okay, something very high happens in a very short period of time. So this is a spike. So the reason of this spike, it can be from lighting, it can be from power lines. When you turn the power on, when you turn the light on, the switch can make some kind of this kind of spike. What is very bad, what is really very bad about this spike is the fact that it is high energy. Because if it is high energy, it's almost gonna destroy your signal completely. You get what I'm saying? So at this period of time, there may be no communication at all because you completely destroy the signal. This is a bad thing. But the good news is this one is just for a short period of time. Just for a short period of time. You got what I'm saying? Any question? Yes, you still have question? Noise interference. That's a very, very good question. The answer is yes and no. Okay. It is yes in impact. Okay. For example, when I told you about collision before. So yes, we have a signal here, and then I'm going to transmit. So when you transmit, so actually it's going to be signal plus signal. You are going to distort it. You got what I'm saying? So this is the impact is going to have here is exactly the same impact we have here. Okay. So this is one part. The other part, noise, I can avoid collision, right? Or I can avoid interference by the proper design of the system. I can avoid it. You got what I'm saying? However, noise, this is something naturally I can't avoid it. You got what I'm saying? So the answer is yes. Regarding the impact, but regarding the cause of it, the answer is no, because this is something I can avoid. This is because of I didn't make the network well, or the design is not well. Or because I need to run a mechanism to avoid it. You got what I'm saying? Which one? Yeah, it always this is out of my hand. You got what I'm saying? This is something naturally. I'm not going to ask you in your home. You don't turn on the fridge or microwave or motor because to avoid making electromagnetics. You get what I'm saying? All of these devices are making electromagnetics around us. The next thing I want to teach here, should I worry too much about the noise? You got what I'm saying? Okay. Or the impact of this noise. Usually I don't care much about the noise. Usually I care about the ratio, how much power the signal has and how much noise you have. Usually we care about the ratio. I can give you a very quick example to understand it. If I have $1 billion, okay, I'm very rich guy, I have $1 billion. If I lose $1,000, it's nothing for me. It's not going to impact me. You get what I'm saying? So, however, if all what I have is $2,000, $3,000, and I lose $1,000, yeah, this will have a big impact. So it doesn't matter how much money you lose. What matters is the ratio. It's the same thing here. So you may have too much noise, but it's okay. Maybe you have little noise, but it's bad. Get what I'm saying? Because I care. That's why we have the term signal to noise ratio. So the signal to noise ratio is actually the average signal noise divided by the average noise power. So the signal power divided by noise power. And also I can express it as a ratio this way, or I can express it as decibel, in decibel this way. Okay. For sure, I don't need to tell you the higher the signal to noise ratio, for sure the better the communication. We always look for higher signal to noise ratio. Is that okay? And this is maybe one way to eliminate the impact of noise. So if you have too much noise, I can increase the power of the signal, okay, to counteract the effect of the noise. Got what I'm saying? Because at the end of the day, we only care about signal to noise ratio. Okay. So I show this exactly the example I give to you. If I have a noise this way, because the signal, we have a large signal to noise ratio, the signal is not very distorted. So this one is very close to this one. However, if in case of the signal to noise ratio is small, so it's going to be very distorted. Maybe you may not even be able to do the communication. Okay. I have here two straightforward examples about the signal to noise ratio. In the first example here, I give you the power of a signal is 10 milliwatt and the power of the noise is 1 microwatt. What is the signal to noise ratio as a ratio and also as decibel? So this is just a very straightforward, but there is a very small trick here. The very small trick is this one is milliwatt, this one is in microwatt. In case of a ratio, they should be the same. So both of them can be micro, or both of them can be watt, or both of them can be microwatt. It doesn't matter, but they have to be the same. Okay. So what I did here is what I did. So you can first of all, you can convert both of them to watt. This is one thing. So I can say 10 to the 10 times 10 to the power of watt. So this actually means milli. So milli, I can remove milli and put 10 to the power is -3. Same thing for micro, as you know. So this should be 1 times micro 10 to the power -6 watt. Is that okay? And I think I can divide them together. Or I can keep this one in watt and I can convert the milli to watt. That's what I did. So how you did it? So what I did here, milli is going to be 1000 micro. Okay, this is very easy, this converters, okay? So what I did here, 10 milliwatt here, as you see here, is similar to 10,000 microwatt. It's the same thing. Again, what's important, ratio should be the same. So you can see here, the ratio here between the signal and the noise, the ratio is 10,000. So the signal is 10,000 times bigger than 10,000 times of the noise. You got what I'm saying? Here, I ask you to convert it to decibel, so it's going to be 40 decibel. So when I tell you the signal to noise ratio 40 decibel, it means 10,000, it's 10,000 times. Okay. I have here imaginary situation, okay? For sure, in life, always we have noise, always. So we have here, we have some kind of imaginary situation here. So here, assuming somehow I was able to make the noise 0. Okay, if this is the case, if you can make the noise 0, which for sure it's impossible, but just for imagination, okay. So here, if I can make this one negative, so that means the signal to noise ratio is infinity, right? And this one also is infinity. Again, this is not realistic, but at least we can learn that the higher the signal to noise ratio, for sure, the better the situation. Any questions? Okay. Next one here, I'm going to talk about data rates, which is bit per second. I already explained a little bit about it. We always, and that's what we are going to see in the coming chapter. By the way, I have posted chapter 3. So that's what we will see in chapter 3. We are interested to get a relation between bandwidths and between in the bit rate. Okay, we all are interested to find this one. You should understand as I increase in, okay, bit rate, that's great, for sure, that's very good. As I reduce the bandwidth, that's good. You can think about bandwidth like the cost. What is the cost? How much bandwidth? So if I give you some bandwidth, you want to maximize the bit rate given the bandwidth you have. You know what I'm saying? So the higher bit rate is good. The lower bandwidth, it's like a cost. This is a cost. You got what I'm saying? So the higher and always you can find the relation is if you need more bit rate, you have to get more bandwidths. You got what I'm saying? So if I have a range of frequencies, if I have a range of frequencies, if I give you this amount of frequency, so you're gonna get a certain bit rate. If I give you a bigger chunk or a bigger bandwidth, more frequencies I give to you to use, so that means you are gonna have higher bit rate, faster communication. That's always the case. We did, if I'm gonna go back, because we did something very rough approximation I did before. Just I want you to remember it. You remember when I did something like that? This was very rough approximation, okay? But at least it can give us a limit. So if you see here, what I did here, I said this is a square wave. Here I'm gonna use sine wave to approximate this one. Okay, for sure. I told you before, this is very rough because this sine wave is not close to square wave. This one is closer. This one is much better. You got what I'm saying? But unfortunately, as you go here, you need more bandwidth. Okay, but anyway, so if you go with the very rough situation, very rough here approximation, we found that the frequency is n divided by 2. That means bandwidth or bandwidth you need is actually n divided by 2. N is the bit rate. In other words, the best thing you can do, N is equal double the bandwidth. This is your dream. This is that's why we call it a limit. This is my limit. Give it, sure, give in this situation, you cannot get bit rate higher than double the bandwidth. Okay, you may get less, that's okay, because this signal is not perfect, but this is the limit we have here. You understand what I'm saying? Okay, but again, this approximation was for a specific case when you have two levels. You know, I can increase the number of levels. That is why I'm going to continue discussing this point here, but I'm going to explain to you a more general case. This one was like a specific case if you have 2 levels. What about if I have 3 levels, 5 levels, 4 levels? So that's what I'm going to give you general case, and I'm going to choose a general case is exactly same thing like this case, okay? But this one is for one case, the other one is general, okay? So that's what I'm going to do here. So what I'm going to do here, again, we are also always interested to calculate the bit rate, always, okay? And get the relation between it and the bandwidth, okay? Here we're gonna talk about two main formulas. The first formula we call it Nyquist, this one, and this one was made for noiseless channel. The second one we call it Shannon formula, and this one was done for noisy channel. Do we have any noiseless channel? No. So why we study this case if this is it's not going to happen? Always we have noise, right? We study this case because this one is going to give me the limit. You can understand what I'm saying? So this is your limit. If everything is perfect, if everything is nice, okay, this is your limit. In reality, you are going to get something lower than the limit. Why? Because we have noise. So this one gives you like a limit, okay, to understand what limit we have. So I'm going to teach here 2 formulas, okay, to understand, to calculate the relation between the bandwidth, okay, and also the bit rate. And also I'm going to show, this is the interesting part, I'm going to show later, although when this will give you what you can get from it is exactly something you can get from here, but in reality you are going to need both of them. I'm going to tell you why. In reality, we need both of them. So let's start with Nyquist. So Nyquist, this is the formula we have here. The bit rate, which is N, is equal to times the bandwidth times log to L. Log to L. L is the level, how many levels you have. So here, for example, how many levels here we have? 1, 2, 3, 4. 4 levels, okay? So 2 things I want to teach here before I end this lecture. Number 1, this formula is not different from the formula I taught before. It's exactly the same thing. But what I taught before, I told you N equal to double the bandwidth. And in this case, L was 2. So if you plug in L here, you are going to get 1. Because you know from logarithmic, log A of A is equal to 1. You know that, right? So log 2 of 2 is equal to 1. So this formula is going to give me the formula I already explained to you before, but this one is more general for any L. The other one was only L was 2, right? So this one for any L. So this is number 1. Number 2, always you can find if proportional relation between bandwidth and bitrate. The more bandwidth you need, so the more the more bitrate, and that's what I need, right? Bitrate. Again, you should see the bitrate as this is the gain. That's what I need, right? You see bandwidth as the cost. How much bandwidth you need from me? As I minimize the bandwidth, if you take very little bandwidth, but you can get very high bit rate, okay, then you'll be happy because this is a cost. Bandwidth is the cost, right? So anyway, so this one is going to be double the bandwidth, okay, times level, okay. The last thing I want to teach here, very interesting, is okay. You tell us the bandwidth is the cost. Okay, so I can simply fix the bandwidth. I'm going to ask the network, give me this bandwidth. That's okay. And then you are telling me something very interesting here. By changing L, I can change the bit rate. And that's what I need. I want to increase the bit rate. So for the same bandwidth you will get to me, I can have very high bit rate. Theoretically, the answer is this. Theoretically, the answer is this. Practically, the answer, unfortunately, is no. Why? Because theoretically, yes, as you increase N, you can increase the bit rate for the same bandwidth, and this is something great. However, in reality, as I think I explained something like that before, in reality, if as you increase L, practically that's not possible. Why? Because as you increase L, the receiver is going to be too complicated because the receiver has to differentiate between too many levels, and this is usually too difficult, too complicated. So there is a practical restriction on how big L is. You got what I'm saying? Any questions? So I'm going to continue next time. Let's take the attendance quickly. I'm sorry.